Okay, recall how we get the table for log base 2 of x. We start with the table for 2 to the x. So that, for example, if x equals -2 and y equals 2 to the x is 1/4, on the table for the log function, columns reverse. So if x is 1/4, y equals log base 2 of x, which would be log base 2 of 1/4, is -2. Okay, so the equation 2 to the a equals c. What does that mean? Well, it means you've got a here, and 2 to the a is c. And that means that on the table for the log function, when x equals c, y equals log to the base 2 of c is a. So here c is 2 to the a. Here a is log base 2 of c. This means that 2 to the a equals c says the same thing as a equals log base 2 of c, because this implies this. Okay? Also, log base 2 of 2 to the a equals a. And of course we just see that from the, here's 2 to the a, and here's log base 2 of 2 to the a. Okay? And also we have log base 2 of d is log d over log 2, and I haven't proven that, haven't explained why that is, just telling you this, and this is much more complicated to understand than this or this. Okay, so these are the basic things we have to work with when we're dealing with exponential functions with base 2 and log functions with base 2. Now we can extend this to other bases, but we're not going to do that just now. Let's just get used to what we can do with log to the base 2. Okay, so what if we have the equation log to the base 2 of x minus 3 over x plus 5 equals 3? Well, this equation is in the form of one of the expressions over here. Can you spot which one? Well, clearly it's this expression. We have a log base 2 of something equals something. We have a log base 2 of this something equals this something. And the something we have inside of the log base 2 function is what we'll identify with c. So c is going to be your x minus 3 over x plus 5. And the thing that the log base 2 of something is equal to is going to be a. So a is going to be 3 in this case. So we have these identifications, so we can use these expressions in this form, which is totally equivalent to this form. So the form 2 to the a equals c, which is equivalent to log base 2 of c equals a, gives us 2 to the a, which is 2 to the third, equals c, which is your x minus 3 over x plus 5. Now, in this form, it's easy to solve this equation. We can find our value of x. We simply, first, let's just reverse sides here, so the x's are on the left. 2 to the third is 8, so this is clearly the same as this equation. We multiply both sides of this equation by x plus 5, and you shouldn't skip steps when you simplify this, but we end up with x minus 3 equals 8 times the quantity x plus 5, which is 8x plus 40, etc. And then we can solve the equation easily from this point. We're going to add a negative 8x to both sides. We'll get 7x minus 3 equals 40. So that 7x then will equal 43, and x will be 43 sevenths, 6 and a seventh. Very easy to solve from this point. Another way of doing this is to say that since log base 2 of x minus 3 over x plus 5 equals 3, then 2 raised to the log base 2 of x minus 3 over x plus 5 equals 2 raised to the third. In other words, 2 raised to this side equals 2 raised to this side. And where does that get us? Well, the 2 to the x function and the log base 2 function are inverses. That means one undoes the other. So this undoes the log, leaving us this. And you can kind of look at it like that. Of course, that's justified by the fact that 2 raised to the log base 2 of a equals a. So this rule applied to this expression, a would be the x minus 3 over x plus 5. 2 raised to log base 2 of a equals a. 2 raised to log base 2 of this a equals this a. And we get this equation. And it's identical to this equation and solved in the same way. So there are two ways we can solve a logarithmic or an exponential equation. Okay. Now, another thing we looked at is just estimating a table of logarithms from a good graph of the log function. So we want to estimate log base 2 of 2, log base 2 of 3, log base 2 of 1.5, log base 2 of 2.5, and that would actually give us numbers to put in the table. So we have 1.5, 2, 2.5, 3. We want to see the logs of the base 2. Well, log base 2 of 1.5, well, here's 1.5. Here's 1, here's 2, here's 3, here's 4. Here's 1, here's 2. And here's -1, -2. We're not using those for this set of estimates. Log base 2 of 1.5 means we look at 1.5 here on the axis, x-axis, halfway between 1 and 2, project up and over, and it looks like that ought to be about, what? You know what I wrote down here? I think I saw the 1.6 up there, it's 0.6. Okay, so we project up here and over. It's a little more than halfway between 0 and 1. So I'm saying that's about 0.6. So log base 2 of 1.5 would be 0.6. Log base 2 of 2, well, it's kind of a no-brainer because that leads to a point directly on the graph, one of the points that we plot when we plot the basic function. And that's going to give us 1. Log base 2 of 2 is 1. 2.5, okay, a lot of people estimated 1.5. Okay, and that's not far off. It's not a bad estimate. Turns out it's actually about 1.6. So it's not too far off, but if you think about it, it doesn't totally make sense because 1.5 is halfway between 2 and 3. The y-coordinate, talk about something different. Let's look at the log base 2 of 3. Okay, that's one that clearly doesn't make a lot of sense. Okay, log base 2 of 3, people estimated, since 3 is halfway between 2 and 4, it's sensible to say that the log should be halfway between the log of 2 and the log of 4. Well, the log of 2 is 1, the log of 4 is 2, base 2 log of 2. Okay, so our log value is 1, our log value is 2. 3 is halfway between 2 and 4, so the log value of 3 you would expect to be close to 1.5, and that's true, it is close to 1.5. However, the graph isn't straight here. You have more slope here than you have slope here, and if you think about it, that means that both of those observations mean that the value of the log base 2 of 3 is going to be a little more than what it would be if this was a straight line. It's going to be a little over halfway between this and this, so we estimate maybe 1.6 or 1.7. Turns out that 1.6 is a pretty good estimate. I think it's 1.58 something. Okay, and then the 2.5. Well, halfway between 2 and 3 is 2.5. Halfway between 1 and 1.6 is 1.3. Now, I made an estimate here based on what it looked like in the graph, and it actually looks more like 1.3 than 1.4, but I put 1.4 down with a question mark. Actually, a reasonable estimate from this graph would be 1.3. And it turns out all these estimates are correct to the nearest tenth. And there's a table in the document that I handed out today that gives you logs for all the numbers from, I don't remember where it started, but it goes up to, and I don't remember where it stopped. It gives you logs in increments of 0.1, x values in increments of 0.1, so you can always compare these. Okay. Now, I say this because on your test, you're not going to be able to use a calculator, and if you need the logs to solve like a log problem, you're going to have to be able to estimate them. So you draw the graph, and you can always estimate yourself a table. Okay. And the last thing we talk about is a rational function q of x equals x minus 5 over x minus 7. By analogy with the polynomial, I kept wanting to say polynomial functions, you're going to find the zeros of x minus 5 and x plus 7. And the zeros are going to be at 5 and negative 7. Now the reason we want to know those zeros is those are the points at which the function might change value. Can't change value except going through 0 or going across an asymptote, vertical asymptote. So the only place q of x can change value is if x minus 5 changes its value or x plus 7 does. That's only going to happen as x goes through 5 or negative 7. So the process is very similar to what we do with polynomials. We partition the x-axis at the zeros of the numerator and the zeros of the denominator, because those are the places where the function can change sign. So here's the axis, here's the 0 of the numerator, which is at 5, here's the 0 of the denominator, which is at negative 7. So we have a partition. We have three intervals, negative infinity to negative 7 to 5, 5 to infinity, and you'll understand that if you understood the last assignment in the last class. We want to determine then the sign of this function on each interval. Now I didn't do that, you know how to do that. Same way you would if it's a polynomial function. And then determine the end behavior, and then we can draw the graph. Now, what I will be asking you to do on homework for this assignment is just take a simple expression like this, find the zeros of the various factors, partition the axis, and determine whether the thing is positive or negative. And also, if it's 0, the denominator, we know from what we discussed last time, the denominator is going to get tiny, so it's going to go into the numerator lots of times. You've got to get a vertical asymptote at any 0 of the denominator. We want to mark that as well.